Okay. Welcome back, Friday afternoon. Thanks for being here. Last time we were getting started on this case problem. Did I miss something or no? No? Oh, sorry, I thought you were like,
This wasn't a year on.
I'm like, what happened?
I was looking at
Yeah. So we were getting started. First step that I had said we should do is kinematics, and that's where we were trying to figure out how all the motion, how we could simplify like what's connected and how they're connected. But it's just talking about like for one moving part, how does it affect the other moving parts? And that's where we're at today. And we left off saying that the top, that if I move the collar in by, let's say, 5 millimeters, the top should do something like 10 millimeters, like around double that. Might not be the same the whole time, but something. Oh, it's me. I'm like, who's talking back there? I thought it was someone in the classroom. I was like, man, they're so loud. But it's just me talking over myself. Yeah. It's the life of streaming on YouTube, I guess. Cool. And that's where we're at. One thing that we recognize was kind of like we have mirror symmetry. Symmetry is nice because you only have to deal with half of it. And the more symmetry you have, the less you have to deal with. So we're just looking at that right side, and it's the same but opposite on the left side. So if we solve this, then we know what happens on the left side. And I think this was where I had left off, was the positions like of those moving hinges. There's hinge O is like at the bottom, not moving, because that's like on the ground. If that's moving, then we need to move the jack to a different location. So that one's like some kind of fixed location. So then what is RA and RB? Like how do we describe where those things are for this thing? So what do you think? Or did you want to start somewhere else? Were there questions as we're kind of jumping back in? Yeah.
We're just scrolling up a bit.
Yeah. How far?
I just take a look at to see like the DET of that L data. Or down. Sorry.
Down?
Yeah.
Right there? Okay. Yeah.
For me, I think RA have two parts. The first part is along x direction is equal to L times sine theta.
Sine theta?
Yeah.
Yeah.
And the second part is along the y direction is equal to y times cosine theta.
What do we think? Like a cosine theta component and a y and a sine theta component? So anytime you have like something moving in a circle, it's always sines and cosines. Like, so each component is going to be sine and cosine, which is what we have with that hinge A. It's like rotating. So depending on where we say theta is, right now theta is vertical. So if it's 0, it's straight up. If it's 90, it's laying flat. So it's just figuring out like what that triangle looks like. But sine, cosine is always describing circular motion. Cool. How does that look? And that kind of comes back to, we were saying like D here was this distance, and we were trying to figure out like how does D change as angle was changing. And really it's just describing what is the x component of our position A, of that hinge A. Kind of nice when things like work out that way, right? All right, so we know where A is. Try writing down what you think B is, and then we'll check back in. Where's B? You already know?
I mean, I just put down 2L cosine theta.
2L cosine theta?
Yeah, because I'm just imagining, like, if you're talking about the distance from O to B, then we can just multiply 2L cosine theta.
2 times that L cosine?
Assuming theta is
Yeah.
the general coordinate.
Yeah, that's our like one coordinate, right? Catching up. Yeah.
Guys, can I have one more?
Yeah.
Previously, you were supposed to be
Yeah.
in that direction.
That makes sense. Yeah. So then that's like the I component. Yeah.
This origin.
Yeah. Yeah, so we can say 0 plus.
0 plus.
Yeah.
Yeah.
That way we have like the magnitude direction always the same direction.
Yeah, I was gonna add this, like, so I was just-
Yeah, that's trying to catch up.
How does it determine that?
I got the ones that's half of all. Yeah, so this is actually, so what's the answer?
Yeah, so normally I like to have the x-axis be 0 angle, and then it's always cosine is x and y is sine. But in this case, what do we think about 0I 2L cosine theta? It jives. Feels good.
Y is equal to 0.
Y is I.
I mean, y in the RP, y the first part equal to 0.
This part? Sorry. Y is this one 0?
Yeah.
So in this case, in order, do I have?
Ah, yes.
Yeah,
Thank you. Nice.
yeah. So we're describing like a vertical arrow. So no matter what the angle does, it's only gonna ever move up and down. Cool. So what we did here was we described all the moving parts. So O is not moving, A is moving, B is moving. Now we can describe like any piece, because if we want to look at like where is that top arm, like where is this thing? Well, we would connect A and B, and that is that top arm. And if we wanted to know where's the bottom arm, it's like, okay, we'll draw from O to A. I know where everything is. So that's why we're going through this exercise of like, where is everything? And not just where is it, but where is it in terms of theta? Like, so as the angle changes, since that seems to be like our main variable, like we're turning a screw to change where that A position is, like how wide it is, but really it's just changing what that angle is. So if we know everything in terms of theta, then we can determine everything else. All right, how fast is everything moving? This one we started to touch on last class, and we used the chain rule to figure it out. Like, what is that distance d, which is one of the components of our positions that we just figured out. So we're trying to figure out what is velocity of A and B in terms of theta. Yeah, I like that. Okay. So same as position, like velocity is going to have, because it's moving in this circle, it should have two components, some x and some y component. We can look at what is the position, how does the position change over time. Yeah. Yeah, like it does, like as you're kind of screwing it in, it's both moving this way and.
Yeah, for some reason, I thought it was compressing but not changing.
Yeah, yeah, you have like kinematic locking, right? Yeah. Do you agree with RP?
Yeah, just
Yeah. optimizing carjack. What did you have? Were you waiting for?
I had L sine theta, and then if theta is a function, then times the derivative of theta.
Yep.
Plus, well, L cosine would be the first term, and then minus L sine. I'll just say it. L cosine theta times the derivative of theta if it's a function, and then
Yeah.
minus L sine theta.
Yeah, so this whole thing. Kind of like this. How does that look for people, for everybody? Similar?
Yes.
Yeah. And so main thing was like, and this usually trips people up. Dynamics is weird because all the variables are a function of time. So whenever you say like, take this derivative, you're not taking like a ddx, you're taking a dx dt and then doing ddt. ddt means the end. Yeah. And then down here, oh, yeah. We still, it can only move up and down, so we're never gonna have left-right velocity. That's good, derivative of 0, still 0. And then we have our 2L theta dot. I guess it's a negative, right? Times that sine theta. Cool?
Yes.
All right, let's do a quick sanity check. If the angle, if this thing's moving up, is the angle increasing or decreasing? If we're turning the screw, decreasing? All right, so we're decreasing. So for a negative theta, what's happening to our hinge A as we decrease theta? Is it going up or down? Should be going up. So a negative theta dot. So if I have a negative theta dot times a negative sign, I still have a positive motion. That's good. And then same thing here for, if I have a negative theta dot, I still have a positive y motion for the top one. So we're doing something right. We might be crazy, but we're at least getting our signs right. I had a friend in grad school who never used plus or minus signs. And I was like, well, that's crazy. How do you keep track of the equation? He's like, well, you keep multiplying it over and over, so half of the time you're right. And I'm like, what? It's crazy to me. It like drove me crazy. Had to like go in his notebooks and add minus signs.
Can I have one question?
Yeah.
So how do you define the sign of the theta?
Sign of theta?
Yeah. How do you know the sign is minus or positive?
Like overall, like what the angle is, or the theta dot.
I mean how do you find the sign of the theta?
Oh, sign.
Yeah. Because
Like S-I-N-E sign,
Yeah,
not
yeah.
S-I-G-N. Yeah. How do you find it? Usually, like,
because you said that when theta is minus and theta is positive, but I'm confused. I don't understand how do we define the sign of the theta.
oh,
It's the angle's decreasing from like the stationary point. So like if this is the initial like drawing of it, if it's smaller, if it ends up being smaller than that, then it's negative. If it ends up being greater. So you see like the initial angle right now, theta.
Okay.
If we turn something or like we move VA in, the difference is going to be like once the after that's gonna be smaller.
So like if it's starting off at 45 degrees, then sine and cosine are both 1 over root 2. And yeah, as we decrease the angle to 40 degrees, everything's gonna, A moves up, B moves double up.
Yeah, because in my opinion, I think to define the sine of the theta, we need to define along kind of the direction of the counterclock or counterclock, something like this. It along to the
Yeah.
counterclock, yeah, something.
Oh, I see. So in this case, at least the way that we drew this diagram, theta is, if it's 0, then the thing is vertical. And then as we add the angle, so counterclockwise, so if theta dot is positive, then we're actually unwinding the thing back to 0, or back to 90. Right? Yeah, so 0, and then increase the angle to 90, which is, again, like, normally what I like to do is everything, like, always theta is drawn from the x-axis, but it's okay. We can do it this way. We can do it. It's our diagram. We just don't want to design it so that we have to lift the car sideways. That would be a very strange jack. Just like turn your car sideways and then start using the jack. It's just, it works better for my coordinate system if you turn your car sideways. Cool. And then I swear I put in values for like, why does it just say undefined? Reducing the angles, link arms are, why? It's supposed to say L equals something, but it's just, why does it say undefined? Yeah, this is what we're supposed to be looking at. So I'll have to go in and edit this so that we actually have like numbers to deal with. So we have L is 20 centimeters. Then our so we know L is 20 centimeters. And I'm trying to see if I specified what the V of the collar was, or if that's just for us to choose. We can choose it. So we can approach this in a couple of ways. One, we could say the angular rate has to be a certain thing. Like it's got to rotate at a certain, like as I'm twisting this thing, it's got to have a constant angular rate. Or we could say that the car has to lift at a certain rate. Main thing is, can we specify both though? That's a question for us for you to think about. Can you say the car has to lift, let's say 10 centimeters or 1 centimeter per second, and the angle is going to be whatever, 30 degrees per minute? Can you do both? Can you specify both?
Yes. Because
Okay.
we can like change the amount of threads that are like rotations per minute, I guess. by
Oh,
changing
okay.
Threads, but if you're trying to like do the velocity in terms of something other than time, it might be tricky.
Okay. Yeah, so I guess you're thinking of like the omega angle of like how quickly we're rotating our thing. Yeah. Okay. But that one's going to be a different theta than our theta. Like if we rotate it 90 degrees or 180 degrees, it's not going to move our angle.
The same amount,
Yeah.
But that speed depends on, makes like the actual thing move, so
Okay.
it's dependent on what we choose that to be, which depends on.
Yeah, so we have some wiggle room in terms of like how quickly we're manually doing this thing and how quickly, but once we say like the pitch is this, can you turn the crank but also have something move at a different speed, like specify 2 speeds at one? No.
I don't think so.
No. This is the fact that we have a 1 degree of freedom system. Like we have 1, 2, 3, 4, 5, 6. So 6 different moving parts, but they have all these constraints that they have to move together. Even the left arms and the right arms. Like if I change the angle of one, we're assuming the other one is just going to follow it. So there's a lot of constraints put on the system by us, like the engineers kind of designing it, but so that the more freedom you have, like it's not like freedom like it's so easy to use this. Now you have a car jack that's like falling apart and you need multiple support structures to like keep it in place. So it's nice to have single degree of freedom systems, at least for this. How long does it take to lift a car when you're using a car jack? When's the last time you changed a tire? I'd give it like, I don't know, if you're like constantly working, 2 minutes. How does that sound? More? How long? 30 seconds? Yeah? Oh wait, are you pumping or are you doing the hand crank?
Oh, I don't have a hand crank.
This is a hand crank.
Hand crank, yeah, with the pump. I mean, hydraulic pump is way easier than the hand crank. Yeah, the pumps get a lot more mechanical advantage than the actual mechanics.
I'll give it 30 seconds.
30 seconds to like crank it?
Yeah.
All right.
This says this out.
So So what do we think? We think we can go from here.
I think we should have an experiment.
That's what I think. $30 seconds? You think 30 seconds?
Is that too?
I would say 2 minutes.
Yeah, because there's actual resistance in the car.
Yeah,
So
it's not easy.
Like,
You're also not lifting the whole car.
Yeah, it's just it's a quarter of the car. Yeah.
Well, it's
Still a
more like a third in terms of how it.
Yeah, so
typically
Correct it.
You think a third?
It's closer to a third because you're lifting up on one side unevenly, so it's not like.
Yeah. Yeah. That's true. Yeah, it's not directly under the wheel, and the car is not exactly like center of mass in the center of the car.
Yeah, but you're not lifting it up directly, you're turning something.
Yeah.
The
No.
car does like one of these.
Yeah.
Up.
Yeah, I would be interested to put a scale on every wheel and know, like, or even just a scale under the thing to figure out how much weight is actually being lifted by it. I said a quarter of the car, a third. I would take a third. Really, for factor of safety, say half the car, and then you get the Yahoos that are like put it directly in the middle and try to change both tires at one time. But so we'll call it 2 minutes. So what is this distance to go from like here to here? And we'll call it capital H. How high do we need? How far do we need to go in 2 minutes? 'Cause that's going to be our number for like a reasonable estimate how fast everything needs to move in order for us to get this thing where it needs to be. Yeah.
Are we assuming that we start at like both legs flat, so 90 degrees, and then going to 0 degrees?
That is a good question. Do we want to start totally flat and then 2 minutes to get it total?
Depends on how someone wants to
Vertical?
store it. Let's just use yeah, I would store it flat, so that you know.
Yeah. I mean, like you don't contact the car until it's until the angle's somewhere around like 30 or 40 degrees, and then you actually start lifting the weight. But like with and without the weight, you can only rotate it so fast, so you're kind of limited by like how quickly you can turn a crank. Most human like ergonomics is like around 1 rotation per second. You can push it a little faster to like 2 rotations per second. It's a little uncomfortable. If it's too slow, like 0.1, then it's very like muscle fatigue, like now you're saying like deadlift, that sort of thing. It's leg day, sort of like, yeah. All right, so how far does it move from like bottom, say like bottom to top? We can call that 2 minutes, right? Oh, okay. What's our max height? Like how high can this thing get?
2L.
2L? Yeah? 2L? How tall is that? 40 centimeters. Okay, so let's say we can do, if we can do 40 centimeters in 2 minutes, that should be fast enough to lift the car without someone like losing their mind. I'll put little arrows to say like average speed, or we could call the average the actual. We're engineers. The average is the real. Have you noticed that? That like engineering, once you get the average number, that is your design. It's like you just design around the average. You'll note, yeah. Start looking, as you start noticing, see like the average is just like the accepted number. If you're in failure analysis, the extreme results are like the worst case scenario. That's what you design around. If you're a scientist, then the best results are what you design around, like best case scenario. All right, so how fast are we moving? meters per second. Because that's what we got to do, meters, radians, seconds, to get it back into like math mode. 40 centimeters, 2 minutes. How fast are you moving?
Point 003.
That one would be if we do 40 centimeters in. Oh, I think that one's meters per minute.
Oh, right, that's minute, yeah.
Yeah.
Minimum, we're gonna I'm not. No, that's it. We could. Maybe, yeah, maybe. I just do active time.
Yeah, I was multiplying that right.
Yeah, yeah. I don't have Yeah, I'm gonna get one back there.
Bro, like the one in the shop.
I got one in that truck and 2 jack stands.
Justin, I think you're experienced enough to say that 2 minutes is legal right now. With like a SMB jack.
Realistically, like 45 seconds.
Now you gotta,
Yeah, but you just have to try it.
But I'm saying you don't even grab an impact.
10 seconds.
Zero, zero.
Yeah, it's
0.03, something like that.
Yes.
Zero, 0.003 meters per second, something like that.
Yes.
All right. Sounds good. Seems reasonable. What is theta dot? There's 2 parts to this. One question is theta dot, do we even know how to find theta dot? Second part is it a constant number? Yeah.
can you use the like derivation you did earlier with the VB?
Yep.
Related to that?
So we can say that we know like this magnitude that we just figured out, like how fast the car is going, that is there's only one component for VB. 2 times 0.2 and then cosine? No, sine. There we go. So we can write that one out. Oh, if you could see it, that would help. Yeah,
Should it be negative 2 times 0.2?
that one should be negative, yeah. Negative, like that. So how fast is this thing rotating if we have a constant kind of speed like this?
Shouldn't it be constant as well?
That it is constant? What do we think? constant speed up, so theta dot is a constant. Okay, all right, so then maybe it's constant. So how fast is it rotating? Shouldn't be that fast, right? Should be some like it should be decreasing at some rate. We can try it. So what is it? How fast are we? Yeah.
So it's the slope of it's a change in the theta, correct? So
Yes.
wouldn't it basically be like our final minus our initial equal?
Yes. So if it is changing at a constant rate, then we could use that same thing that we just did here. Of like, okay, take max minus min, divide by delta t, and we could say that. Yep.
So what is the unit of the theta dot?
The theta dot.
Yeah.
So we're trying to figure out like
Yeah.
how quickly this thing is like folding.
No, I mean, what is the unit?
Oh, unit. Units are always gonna, for at least when you're doing like kinematics like this, units are always radians per second. I know calculators have degree mode, like you can kind of switch back and forth. Technically, it's introducing units into a unitless measurement. So radians are the only like unitless degree measurement, like angular measurement. So when you talk about like how fast something's rotating, usually it's radians per second because that's a meter per second. Circumference over diameter is that ratio. Did anyone come up with number? Yeah.
Well, when angular velocity depends on theta,
Depends on theta. What? But it's constant. We just want a constant. No, I like it. Yeah, I agree. It depends on theta. So we have 0.003 equals 0.4 times sine theta times theta dot. So I'll take all this and that sine theta didn't go away. Like we still have sine theta component.
Is it because of its reliance on VA and VA is moving like curve?
Yeah, so VA, like the way we're actuating this is like with two intersecting circles. Like as we move something along one circle, we're drawing another circle. So we can't get rid of the fact that there's like sines and cosines there. But that's okay. I know this isn't like 90 degrees, but let's say that. Let's say like when we're totally flat and we want to move the thing up when theta is 90, how fast is this thing? How fast is the angle changing? This will give us like the range of values of like what the theta dot is.
One side is just 0.003 over
0.003 over that 0.4. Is
Is it still negative?
that one?
Yeah,
It's the negative from.
Yeah, you're right. Yep. Thanks.
You multiply it. Yeah. Plug in that.
And what would that be? -3, -1, -2. Think like that.
Person in the chat about it.
005. Yeah, nice. What about when theta dot, what about when we're like right at the top? Like basically there. Theta 0. What's theta dot? 0?
Yeah.
0
It's like a limit there.
is a limit. Okay.
Math limit.
Math limit. Okay, I like this. Math limits are good. What's the math limit?
It's like on the point, but technically like the real rules, like that's the math.
Yeah, so we can't really get it to keep rising at that point. What if we're like almost there? Like it's not 0, it's like 0.0001, but we're still moving at a constant speed to get up there. How fast is the angle changing to get us there? Is it real close to 0?
It's like real close to 0.
You think real close to 0?
Or, yeah, so sine 0 is 0, so you'd be dividing by 0, so its limit is infinite.
Should be the opposite of 0. Yeah, 1 over 0. So something's going to 0. It's the sine theta. If 1 over sine theta goes to 0, or sorry, yeah, if sine theta goes to 0. Sorry.
Denominators get like really small, change rate changes.
Yeah, so as we're like getting towards the top, as we like keep trying to say, all right, keep going at a constant speed, we're gonna need to snap this thing. I mean, again, it's all of like a millimeter or so, but it's gonna have to move really quick to keep up with this constraint that we just put on there. Oh yeah, let's put some units in here. Once you have infinite radians per second, just use degrees or whatever. It don't matter. It's infinite. You can add some units or subtract them. You could use hertz. Cool. Thanks a lot. Have a great weekend.
Thank you.
It should be nice tomorrow, so enjoy some sunshine.
For once on Connecticut weekend.
Yeah.